Let me know if you guys can't hear it.
It was the year 2000. An application developer named D. Richard Hipp was working on damage control software for US Navy guided missile destroyers. Yes, a terrorist attack was about to change the world as we knew it, but the bigger problem was that the app Hipp was building relied on a SQL database, and whenever the database server went down, his app would too. So he asked himself a simple question: can jet fuel melt steel beams? Wait, no, that's not the right question. He asked himself, why can't I have a SQL database engine embedded inside the application itself that talks directly to the files on disk? That would get rid of a separate server process, the ports, the configuration, and the neurodivergent webmaster you needed to keep it all running. He liked the idea so much, he gave it a name, spent the next 25 years of his life building it, and today it may be the most important piece of software ever written. But by stripping the database down to a single library that read and wrote to one file on disk, Hipp accidentally made it small and simple enough to drop almost anywhere, which is exactly what happened. Today there are billions, no trillions, of SQLite databases in the world, and at least one on every iPhone, Android, Mac, Windows, posterior insertable, browser, and Mars rover in existence. It's easily the most trusted and resilient software out there, and in today's video, we'll look at a project that's crazy enough to think they can rewrite it from scratch in Rust. It is June 19th, 2026, and you're watching The Code Report. If someone told you they were rewriting SQLite in Rust, I think you'd have trouble figuring out if they were one of the smartest people you ever met or one of the dumbest. In this case, it's two people, and the evidence points mostly to smart. One of them wrote a book on latency, and the other was ranked by Linus himself as a top 5 contributor to the Linux kernel. Their problem was never that SQLite is bad, but rather that it's not truly open source in the traditional sense. The source code is available, and you can do whatever you want with it, but it's maintained by just 3 people, and they don't accept outside contributions. That model is a big reason why it's trusted, but it also means that if you have opinions on how it could be better, you can remove your SQLite-powered posterior insertable and gently return it back to where it came from, or you can keep it and rewrite the library in Rust. So that's what they did, and they're calling it Turso. And the first feature you won't find in SQLite is concurrency. The way SQLite works today is only one writer can touch the database at a time. With Turso, multiple writers can work on different parts of the database simultaneously and only conflict if they actually touch the same rows. Although SQLite has had this on a branch for the better part of a decade, it's never actually been shipped to main. The second feature is Turso async. A SQLite blocks the thread every time it touches the disk. With Turso, that operation hands control back instead of locking everything up, so your app can actually do other things while it waits. Then the third and probably most important feature nowadays is vector search. Every AI app needs a place to store embeddings and find the nearest ones fast. Usually what you do is just bolt on a separate vector database like Pinecone, but now you're running 2 databases with double the complexity. The Turso comes with native vector types and indexing built directly into the database, so your embeddings live in the same file as the rest of your data, and you can query them with the SQL you already know. It's the exact trick Hipp pulled 25 years ago, where you take the thing that's needed in its own server and cram it into a library small enough to run everywhere. Except this time, the thing is your AI's entire memory. But doing more than SQLite is the easy part. The hard part is earning the trust that took 25 years to build. To do that, you need to be a drop-in replacement, and you need to never lose someone's data. The drop-in part is basically done because Turso is already fully backwards compatible with SQLite, so you can swap it in without rewriting anything. But the never lose data part is harder. So to get there, Turso uses a pretty interesting testing strategy called deterministic simulation. What they do is run the entire database inside a simulated universe and play God with time, the network, and the disk. Then they inject failures like power loss mid-write, a corrupted page, or a disk that lies about whether it saved your data, and then replay the exact same scenario from the same random seed until they squash the bug. And because Turso is actually open source, anyone can contribute as you traditionally would. So is rewriting the most trusted database on planet Earth actually a good idea? Probably not, but you're only viewed as an idiot until it works. And speaking of ideas that sound dumb until they work, what if your AI coding agent didn't set your money on fire? And that's why you need to know about JetBrains, the sponsor of today's video. Their Junie coding agent just graduated out of beta and is based on a very relatable simple idea. AI tokens cost too damn much, so they made Junie completely model agnostic and created a lever to decide what each task should cost. You can choose a cheaper model for routine work and a more expensive model for harder jobs. I use the Junie CLI to add role-based permissions to an existing admin dashboard, and I liked how the advanced plan mode creates a full spec in the Junie plans directory with your full project requirements, technical design, delivery stages, and tests. I used a stronger model for this planning phase, then switched to a much cheaper model to implement everything, and save myself a bunch of tokens. Junie just beat out every other coding agent in the most recent SWE rebench, and you can get 20 free AI credits when you use the code FIRESHIP20 at the link.
Okay. Now let's get started. I'll send the GitHub link in the chat. It's in the chat. Let me share my screen. Okay. Last week we worked on our data client, which was getting historical data, getting macro news and ticker news from the APIs. We worked on our helpers, right? Which is parse data, format currency, sanitize file name, time frame to days, and safe divide. And we were working on LSTM predictor, which is a neural network. And yeah, let's continue on with this. And when you guys look into the GitHub, it'll be inside models for project 13. And let me turn on LightShare. LightShare link is in the chat. Open it up. And we'll continue with LSTM predictor. See. Adam, when you're ready, can you share your screen? And we'll continue with lstmpredictor.py.
Okay.
I enabled sharing. Can you guys see it? I'm just at the black screen. Adam, if you're sharing it, can you unshare and then try again to share it? For us, it's a black screen.
My computer is kind of slow.
Oh yeah, take your time. Um, accepted. Okay, so go all the way to the top. You'll see a try except block. Right? Line 15, you see the try. There we're importing Torch, which is, as you guys know, a library used for AI training. And we're importing Torch's neural network, which is NN as NN. No, delete that. I'm just saying. If you see the class defined inside of it, it says price LSTM, right? Line 19. We're defining a new class called price LSTM, and it's inheriting from neural networks module class. That's what that nn.module inside those brackets mean. It says class price LSTM, that's our class. Inside our brackets, we're putting in our parent class. So we're saying we're inheriting from nn.module and we're calling this class price LSTM. What inheritance means is that this child class called price LSTM can use any function or any variable defined in that parent class, which is nn.module. So usually, some analogy that people use a lot is so the parent can be all the animals classes, and a child class can be a dog. So a dog is an animal, right? It's a subset of the animal family. Let's say for each animal, all the animals can have, let's say, an age. Well, the dog, if it inherits from the animal class, can get a variable named age. But it can also define its own variables that doesn't apply to the whole animal family. So dogs itself can have hair, while not all animals have hair, right? Some don't. That's what I mean. Now, how this relates to that, if you go up, price LSTM, we can use any function or any variable inside nn.module, and we can define our own variables and functions, but they can't be used inside nn.module. All right. Now go down a bit, a bit. Now let's read that docstring. So we're building a simple LSTM model for time series forecasting. So the architecture is going to be LSTM layers with configurable hidden size and number of layers, right? You guys know what this is. This is for neural networks, how they can have multiple layers and hidden sizes. Now, the dropout between LSTM layers is going to be if the number of layers is greater than 1, and the final linear layer that outputs a single value. So that output is going to be one single value that we give back. Now, the forward method is going to be those 4 steps. We're going to pass in the input. We're going to take the last time steps output. We're going to pass it through the linear layer. We're going to return that one single predicted value. All right. Go down to define init, line 33. Now for classes, you guys already know init is where we define our kind of global, but inside that class global, kind of scoped variables. So input size equals 1. That means that we can use input size in any other functions inside our price LSTM class. So only if they have that self, right? So let's say like define forward self. Then we can use self.input underscore size inside our forward function, even if it is not defined. Does that make sense? Now, super.init, does anyone know what that is? Line 36. How does it differ from init in line 33? Anyone know? Okay, so it's another object-oriented programming question. So init is basically for defining any variables that's going to be used inside price LSTM. Super init basically means we can now define what we want to use from the nn.module. We can imagine that nn.module is itself a class, right? It's going to have its definition of class nn.module. Now, this nn.module can have its own init function, right? Where it defines its own variables that can be used inside this one, inside that class. Now, for us to be able to use that, nn.module's variables defined in its own init, we have to pull it in. How we do that is by defining super.init. Inside super.init, you would usually define, I don't know, you want to use this function, this variable. But here it's empty, right? Super.init is empty inside the arguments. That means we don't really care about any of the variables defined in nn.module. We can still use functions though. Okay. Okay, let's continue. So delete the pass on 38, line 38. Here we're going to define the variables that we want to use inside our class. So let's do self.lstm. Equals nn dot lstm, and that's the class. So yep, and inside that you're gonna do input size equals input size, comma, hidden size equals hidden size, comma, num underscore layers equals num underscore layers. And comma batch underscore first. Batch, BATCH. Batch first equals true, capital T, true. Comma dropout equals 0.2. Drop out equals you can't do that in Python. No random spaces inside variable names. So for this function, I mean this class, the variable name has to be no underscore for the dropout. Yep, dropout equals 0.2. If space if, no, inside the, why is it doing that again? Go to, so delete the comma and then do space if number if space num underscore layers is greater than 1, else 0. Yep, good job. Do Control S to save it because we want to do this formatting. Now go to up again. Line 45. You're going to find another variable. Tab. Self.fc equals nn dot. Actually, before that, you see line 38, you did self.lstm. Can you make that all lowercase? No, not that. Line 38. Only that one. LSTM lowercase. Yeah. Now go back to line 45. You're going to do self.fc equals nn dot linear, capital L. That's a class. You're gonna pass in hidden size, comma 1. Good job. Now go to pass, the line 48, delete the pass. Out, comma, underscore equals self.lstm, lowercase. That's a it's an instance. Now pass in x. Next line, you're gonna do return self.fc function. You're gonna pass in out, square bracket, Inside the square bracket, you're gonna do colon, comma, -1, comma, colon. Good job. Now, does anyone know what that does? What colon, comma, -1, comma, colon does? Anyone know what this does? Yeah, but more like how do you guys think the indexing works here? You're right that it's like trying to index out the output. Yeah, good job. Wait. Um, I think you're right. No, that's for indexing, right? Okay, okay. You're right if it's indexing, but the -1 and the colon would have been switched so that -1 is on the third index. That's when it does the like opposite side. But for this one, sorry, this one is different because we're calling self.lstm. So basically, for the LSTM, it's gonna have three indexes. First index kind of represents the batch, so how many things we're pulling in. And then second is the sequence length, and third is features. So it's I don't know why I asked you guys, but it's basically just represents data. You can stop sharing, but before you stop sharing, can you control S? Because you have unsaved stuff. Like control S on the, yeah, that's good. Kaden, can you share your screen? We'll do create sequences. Uh, Holy, I'm looking at the next function, predict price. I think we're gonna have to split this like four ways because it's gonna be a big function. Uh, yeah. Okay, let's go up though. You're gonna get the easy one first. Above this function. It's called create underscore sequences. So usually when you guys see the underscore at the start, like underscore create underscore sequences, it usually means that it's like a helper function, so it's like pretty quick, if you guys get what I mean. It's not like does anything too much. Anyways, create sequences, basically you can pass in the data, you pass in the sequence length, and if you read the doc string, it says create input output sequences for the LSTM neural network. For each position I from sequence length to length of the data, we're gonna do x equals data's I minus sequence length all the way up to I, and y is gonna be data's I value, and we're gonna return the NumPy array. Okay, x s comma y s equals, and then two lists. xs comma ys equals a list and a list. Sorry, list comma list, not inside each other. Yep. Next line, you're gonna do for I in range. And for range, it's a function, and we want to pass in SCQ underscore length and comma length of data. Yeah, good job. Next line. XS dot append data square bracket. You're gonna index it to I minus sequence length. Yep. And to 1. I mean, I. Let me see. Yeah, good job. Next, you're going to do ys dot append data square bracket I. Backspace and return np dot array function, yeah, xs comma d type equals np dot float 32. So d type equals np dot float 32. Yep. So it's saying data type is numpy's float 32 variable. No comma there, but comma on the outside the bracket. np.array again, this time for ys, comma the data type equals numpy's float 32. Yeah, good job. That's it. You can stop sharing. Just save the file. Okay. Now we'll do predict price. Didn't Adamant. James isn't doing it. Nicholas, can you share your screen? Nicholas? Nicholas? And... Okay, then Adam, can you share screen? Now go down to predict price. Okay, so this is like a bigger function, right? Let's read the doc string. So we're training an LSTM model for the given ticker and predict future prices. We're going to fetch the past 2 years of historical data. We're going to normalize the close prices. We're going to create training sequences. So 80% training, 20% testing. We're going to convert data to type PyTorch tensors. If a saved model exists, we're going to force retrain false and load it up. Otherwise, we're training a new model. We're going to use the trained model to predict days to predict future values. We're going to denormalize the values and we're going to compute the train and test. Okay, so basically what this does, we're trying to like create a machine learning pipeline for kind of predicting stock prices using something called a recurrent neural network. And this is what a LSTM is. And we're building it with PyTorch. So basically, we're gonna take in a stock ticker, say like Apple or Tesla, and we're gonna pull up the historical data. We're gonna train the neural network to represent patterns over a kind of sliding window of time. Sliding window in like LeetCode terms is having a left and a right index and kind of sliding them, which is why it's called the sliding window. And then we're going to project those patterns into the future and try to predict the next 30 days of prices. So let's get started. Can you go to line 122? So first step is to gather data and normalize. So what you're going to do is tab, and then we'll get started. If not underscore, if not torch underscore, torch is, I mean, torch underscore available, but all caps. Okay, let me kick everyone out of the shared one except Adam for now. 1 second. Actually, on your bottom left, can you see that live share button? Can you click on it? No, not that one. Oh, focus participants opens. Can you click? Okay, what does follow participant? Can you do follow participant? Oh, then never mind. Escape, do it again, but do um focus person. I think that's what. Okay, now let's see if this works. No, it just did it again. Okay, let me then try to do this myself. Focus participants. To follow you. Okay, maybe try it now. So, colon. Okay. Maybe click the black light share. Or the blue light share again. Oh, click cancel on the left. I mean, never mind. Open session. How do I do? Okay, I think it's good now. Try this. Escape. If not, torch unavailable. Enter. Okay, it looks like it's better. Return. Should I make you do this? Oh yeah. Dictionary. So a curly bracket. And the key is going to be a string called error. String called error. String. So quotation. That's the key. Now we need the value. How we map it is colon, right? Value is going to be a string called PyTorch is required. And that's good. Next line. Backspace. History or HIST equals DC dot get underscore historical data. No space underscore. Get historical data. That's a function. You're going to pass in two variables, ticker, comma, and it's a string called 2y. No, number 2y. And next line, you're going to do if error in history. I mean, HIST. Uh, colon, enter, return. No, you're missing a tab and you have an extra slash. Yeah. And you're returning a dictionary. Or actually, just copy that dictionary error PyTorch is required and delete the PyTorch is required. Actually, okay, colon. Now do HIST instead no quotation. The reason I'm saying no quotation is because HIST here is a variable. And we're going to access this variable's error value, but to do that, you need the square bracket here. If you hover on the HIST, okay. The reason it's saying loading is probably because you're like SSH'd onto my local computer. So it's probably going to take some time. But if this code was on yours, it would say it's a dictionary, which is the reason why we're using this square bracket to index it. And to index it, we need to get the key value. The key value's name is called error. So you're going to do quotation error. So you keep trying to do like error without the quotations. That's only possible if we have a variable defined called like error equals quotation error. Then we can do history, index it to error, but we don't have that. So you're trying to do say like some random just for to the computer, it's reading it as just random chars, right? And it's like, what does this do? It can't even read it, right? Now, with this, you're gonna do next line, you're gonna do prices equals HIST, square bracket, quotation error. Next line, you're gonna do, I mean, not error, close. My bad. Tab dates equals HIST, square bracket, quotation, dates. Yep, next line. Okay, when we do this, guys, from like line 121 to 129, can you guys kind of visualize what we're trying to do? Like, does it make sense? So first, what are we trying to do? We're trying to check if torch is available. If not, then we're returning an error, right? Or error handling. And then what are we doing? We're getting historical data for this ticker in the time period, which is 2y, right? We're saving this output to HIST, and it represents the history, right? Now this history, this value is going to be a whole, let's say, dictionary of values. But this history might return nothing because let's say some ticker has no values, right? Then we're going to try to error handle that. We're going to do if error in history, then that means there's an error. So we're going to do return the error, right? No, don't do that because we already have that, right? We already have that in line 125. Line 127, we're doing, okay, if there's no error, then we must have prices. So we're going to try and get those by using the key close and the key dates, right? Now, what needs to happen next? We need to check for errors, right? If length of prices, your turn now. So if length of prices, how do you do that? You need the len function, right? You gotta think about this function, which is no, circle, yes. And then prices. And then length of prices is less than. No, because visualize it. You have the length of the prices. That's integer, or let's say it's an integer. Then you have to compare that with something else. So you have to do less than sequence underscore length. So it's going to be seq underscore length. It's looking kind of hot. Whatever. Length, full English, plus 10. The reason I said full English for sequence life is because we have the variable defined in the arguments. If we didn't, then you could have just said len, but we do. So enter, we're going to do return. The reason it didn't end that for you is because you forgot the colon. You're going to return. It's going to be this like before, right? It's going to be a dictionary. You're going to have error. You're going to say a string called insufficient historical data for prediction. Now, you may be noticing that we have this always returning this same format of dictionary, right? You're having this error key inside this dictionary. The reason is whenever some other function calls this predict price function, it's expecting a error key if there's an error. So every return value should be that same format of dictionary. All right. You can stop sharing and we'll move on to the next person. Nicholas, can you share your screen or no? Kaden, can you share your screen again? Oh, you can. Okay. Uh, okay. Take your time. No, Kaden. After Nicholas. Thank you, though. Any questions so far, though? Nope. Okay. Just know that you guys probably shouldn't use this for actually trading stocks. I know that you guys can't probably right now, but it probably doesn't work, especially at this so lower level. Of course, it can probably give you like some overview, but or also if it was this easy to predict prices, all the banks would do this and it would become instant country level wealth, right? But instead they invest so much trying to build these, right? Okay, let's try to follow you. Follow participant, focus participant. Okay, focused on you. Does this work? What the? Okay. Uh, why is there no if torch? What the? Adam, did you say you probably need to save your
Yeah, I did.
okay. Weird. Okay, then let me get it.
No, I just saved it.
Oh, you just saved it. Yeah, I think it got deleted. Yeah, here it is. Line 133. Let's start there. Tab. Ah, it's moving for you. Can you click that blue light share button, Nicholas? Can you do follow participant? Can you do guest user? Hmm. Okay. Or maybe I have to make everyone follow me. Whatever. Oh, backspace. Okay. Where were we? Okay. Normalized, comma. Why is it doing this? Okay, maybe try now. Still? Can you unfollow me? How do you do that? Can you go to left side? You see that timeline outline and at the bottom live share? Click live share. Right click Andy JB. Unfollow participant. Now do. Now it should work. Okay. Okay. Where were we? Normalized D. So backspace, backspace, D, comma, MN, comma, MX, comma, MX equals underscore normalize. That's a function. We want to pass in prices. Next, we're going to do capital X, comma, Y equals underscore create underscore sequences. That's a function. We're going to pass in normalized, comma, seq underscore length. Next line, you're going to do split underscore IDX, which is the split index. IDX equals integer function, so int, length function, so len. You're going to pass in x, capital X. To the right, you're going to do times, no, outside the circle bracket, times 0.8. Next line. So stop right there. What we're trying to do now, right? We're trying to normalize the prices. You're getting the sequences of X and Y's. You're going to try and find the split index so that 80% is used for testing, 20%, no, 80% is used for training, 20% is going to be used for testing. 80 training, 20 testing. So we have a split index. Now we're going to do X underscore train, or capital X, underscore train, comma, Y underscore train, lowercase y. Actually, why am I doing capital L underscore? Whatever. Equals capital X, square bracket, colon, split IDX. Outside the square bracket, comma, Y, square bracket, colon, split IDX again. Copy that line, paste that to the below it, and replace the X test and Y, I mean, X train and Y train with X test and Y test. Next line, you're gonna do, oh, wait. Right. The difference is that the colon is gonna be on the right side now. Because you're saying up to 80% of the list you're gonna use for training. From the 80% mark to the opposite side, which is 20%, you're gonna use it for testing. Now, let's do capital X underscore train underscore T equals torch.tensor. Torch is all lowercase, is a function. You're gonna pass in capital X underscore train underscore. You're gonna copy that line, you're gonna paste it 3 times. One more time. Second one is gonna be Y underscore train underscore T. So just Y equals torch tensor and then Y train. Under that, you're gonna do replace the train with the test. Under that is gonna be Y underscore test underscore T. Y underscore test. Model underscore path equals model underscore dir, all cap, divided by f string, curly bracket, ticker, right side, inside the string, outside the curly bracket, underscore LSTM, no space, dot PT. Now stop here. You already know 80% of the data is used for training, 20% is used for testing. Now you're getting 4 tensor values for each training data. There should be 4. 2x values, 2y values, 2 training values, 2 test values. And then the model path is going to be what we're saving that model to, which is going to be the model directory. And then the file name is going to be ticker underscore lstm dot pytorch file, which is pt. You can stop there. Caden, can you share your screen? Okay. Model equal, oh, right. Can you also go to, you see that outline, timeline, go to LiShare on the left side, bottom. LiShare, yep. Right click that, unfollow. There you go. Now tab. Model equals next line. Model equals price LSTM, capital P, all caps LSTM. Remember, that's our class. That's a class, so you need the circle bracket. Inside the circle bracket, you're gonna do input underscore size equals 1. Hidden underscore size equals 64. Comma. Num underscore layers equals 2. Next line, you're gonna do if model underscore path dot exists. EXIST. INS need to switch. Yeah. If it exists, which is a function, and not force underscore retrain. Outside the circle bracket. Next line, you're gonna do a try and except block. So try, colon, next line, model dot load underscore state underscore dict. That's a function. You're gonna do torch dot load, which is a function. Model underscore path, comma, map underscore location equals string CPU. Reason being, we do not have a GPU. I mean, I'm gonna assume. Next line, you're gonna do model.eval function. Next line, you're gonna do trained equals true. Capital T, yep. Except exception. Great job for finding where except goes. Colon, enter. You're gonna do trained equals false. Next line, you're gonna do backspace, backspace, else. Trained equals false. Good job. Let's stop here. Okay. You guys can see my screen, right? Yeah. So today we worked on LSTM predictor, right? Here you guys can see the git diff. Oh yeah. If you guys don't know, basically git, you can see the difference between the past code and your code from your past commit to your next commit and the current status. So we can see here in the command line, if I type git diff, then you can see what we added. We have the LSTM code, we have our forward function, we have, what is this? Create sequence. We have predict price. All that, and that's the end. So how you guys go, you guys should try and learn Git. It's a great tool. You guys will have to eventually learn it when you guys go actually work. But yeah. So we did that today. Let's give it a name. Worked on LSTM predictor class. We're gonna stage our commit. Usually you guys can do it in git add dot. Or let's say git status, git add code. Anyways, and then you commit it with a message. I sync my changes, push it. Then you guys, when you guys pull it, you guys will have my change. And in our commit message, we can open GitHub, we can open changes, we can check it out. Next week, we're going to continue on with our predict prices function. And then I'm thinking of going to sentiment analyzer. So basically, we're going to do sentiment analysis of financial news. And yeah, we already did sentimental analysis before, right? So you guys probably know. And let's do a Blicket. Oh, let me stop share. I mean, stop recording.